So today, this is the last session for fluid mechanics and its application, and we will revise all the 12 lectures and solve the numerical problems related to what we had done till date. So just a recap of what we had done. Like okay, so just a recap of what we had done till last class. So initially we had studied about first class we had studied about fluid statics. Then in this we had studied about fluid properties. Then fluid on rest, fluid on fluid in rest, and then in fluid in rest we had studied about forces, stabilities, and then we had also studied uh, rigid body motion of fluid, rigid body motion of fluid. And in then after we studied about fluid kinematics, and in fluid kinematics we had studied about streamlines, streak lines, then path lines, and some acceleration. Then we had studied about fluid dynamics, fluid dynamics, where we had studied of laminar flow. And in laminar flow, it has two parts, external surface and internal. Like external flow and internal flow, it is mainly like this. And then in external flow, we had studied about the boundary layer. And like in these 12 classes, we had studied all this. And also, we had studied about dimensional analysis. So we are going to do the questions related to this. So from the first part, fluid statics part, we will start. So the question is, um, you have a shear stress graph versus a strain rate graph, and it has like you have one graph like this, you have one in this way, one in this way, then one in this way, and in this way, and this is A, B, C, D, E, and you have to name what graphs are A, B, C, D, and E. So as you know, Newtonian, we know that we have two types of fluids. So you need to identify which of the fluids are. So the option are P is rheo, rheopactic, then Q is Bingham plastic, then R is pseudoplastic, and S is Newtonian, and then T is dilated. And you need to match which of these are with each other. Like if like we all know, we have two classes of fluid, Newtonian and non-Newtonian. And in Newtonian fluid, we know that. our shear stress is directly proportional to rate of rate of shear strain or strain rate. So therefore, one option is that your B is your Newtonian fluid. So this is B, and what rest are we need to identify. So from here, if you see that your this A is dilatant, or it is shear thickening fluid. Then your C is what is called as um, C is pseudoplastic, like this is pseudoplastic and dilatant and pseudoplastic. So this is shear thinning fluid. Then your E is Bingham plastic and your D is rheopactic. So this is the type of fluids, and so this is also called as shear thickening fluid. This is called shear thinning fluid, and this is Bingham plastic that is it requires some minimum amount of tau zero. So if I write T is equal to mu du by dy, so I should write it here. T is equal to mu du by dy. This is the relation. For dilatant, it is some and du by dy raised to the power n, and n changes. In the Bingham plastic, it is tau is equal to tau 0 plus mu du by dy, and similarly for also this, it is tau 0 plus mu du by dy raised to the power n. So this is the equation of like different types of fluids. Now the next question is, it says that there is an air bubble is at depth of 10 meter inside sea level of diameter, so 2 mm. So basically the diameter of the air bubble is 2 mm. The surface tension between air and water is, so surface tension between air and water is, so as we know surface tension is the binary property 0.0716 Newton per meter, and you need to find what is the pressure inside the bubble if atmospheric pressure is 100 kilopascal and your G value is 9.8 meter per second square. So what happens is you have a sea level and here you have an air bubble, and this is length is 10 meter, and the diameter of this bubble is G is equal to 2 mm, and you need to find what is like pressure at this surface is P is equal to 100 kilopascal. So for this type of question, you need to first find what is the pressure at this level. Then because of this bubble formation, there is a change in pressure. So I will write P absolute inside bubble is equal to P of ATM plus rho G H, that is this is 10 meter and this is rho L, plus 4 sigma by it is 4 sigma by D because of air bubble, because of the curvature. This is the formula. So PATM is 100 kilopascal, so 110 raised to the power 3 plus 1000 is the density of water into 9.8 into 10 plus 4 into sigma is 0.0716 divided by the diameter, that is 2 mm, 2 into 10 raised to the power minus 3. And if you solve everything, this will come as I think 198.14 kilopascal. Yeah, this is the value 198.14. This is the absolute pressure of the air bubble. Now the third question is you have given you have given uh, a flow over a flat plate, and this is a boundary layer, and this is your flat plate. This is the flow that is happening, uniform flow, and it says that this is region one and this is region two, and uh, which the options are you have one is viscous and one is inviscid. So which of the following regions are viscous and which of the following regions are inviscid? So as you know, when the flow over a flat plate takes place outside the boundary layer, we say that this is inviscid region. Okay. And inside the boundary layer where the viscous force are present and they are dominant, it is called as viscous region. Although although fluid are viscous all over the region, fluids are fluids are viscous all over the region, all over the region. But but because of um, only only a portion of because of only a portion of region, what is say, only a portion of fluid fills the boundary. Now the next question is, it says as the depth inside water tending towards infinity, the difference in center of pressure and center of gravity of a rectangular panel 2 into 1 centimeter square tends to. So it says that as the depth inside the water tending towards infinity, what is the difference in the center of pressure and center of so I should write the center of pressure of any panel. It depends on center of gravity plus Ig upon Ah square. So this is the formula. So here it says that as this this value is tending towards infinity, so you know that SCP minus SCG is equal to Ig upon Ah square, and as h tending towards infinity, this value is very small. Therefore, SCP minus SCG, that means center of difference in center of gravity and center of pressure tends towards zero. So, therefore, if both the water, if if a plate is, suppose this is your layer of a liquid and a plate is placed at a very large distance, so it's if that is there, then the difference between HCP, center of gravity and center of pressure tends to zero. Now the next question is, you have a configuration given for the configuration 1 and 2. So the configuration of 1 is This is your surface level, and you have a square plate of 1 mm. And then again you have a surface level, and you have a square plate in this portion, and this is also the side is 1 mm, and this is all the water is filled, and you need to find what is the ratio of center of pressure. So I should write H of center of pressure of first divided by H of center of pressure of two. So please solve this. I will be I will be coming in 2 minutes. Okay, so I hope you try to solve the question. And so the answer is first, you need to know, as you know, with the formula HCP for a vertical plate is equal to H of CG plus IG upon AH square. Now, if you see here, the IG of this plate along this diagonal is for the first system. If I divide this section by into two, so IG of this section is 1 by 12 H raised to the power 4. So, and if I see the diagonal along the diagonal of this section, here also The Ig is h raised to the power 4 by 12. So this h is the, or I should write it as a raised to the power 4 by 12 because a is the side of the. And now here, if you see what is the center of gravity of the plate, so it is a by 2 because this is half the length. Now here the center of gravity is, if you see, it is half the diagonal length. So diagonal is a root 2 divided by 2. So a is 1 and it is 1 by root 2. So this is the length, this is the, what you say, the center of gravity. So therefore, if I say SCP1, it is a by 2 plus a raised to the power 4 by 12 by a into h square. So a is all again your a square into h square, that is a square by 4. And here it is SCP2 is a, so a is your a by root 2 plus a raised to the power 4 by 12 upon a square into a by 2. So this is a square by 2. So this is SCP1 and SCP2. As you know, a is 1. So if you directly put and if you solve, you will get a ratio that is, if you just try to solve it, uh, it is actually not the ratio but the difference. So the question is SCP1 minus SCP2. Uh, so first this value is coming as 0.824 meters and this value is coming as 0.666 meter. So as you can see, this is large compared to this. So the difference and the mode of that is 0.158 meter. So this is the difference for this configuration. Now the next question is, it says you have a flow on the left, you have a liquid that is stagnant on the left side and a sphere like this is placed, and this is trying to stop the liquid from going out, and it is supported. So if you see the picture, it is supported in this way by a support like this, and the question is, this is a cylinder, and one side of the floor, the radius of the cylinder is 3 meters. The reaction force we need to find out. We need to find out what is the reaction force, this R, and it is given that the vertical force is balanced by the, and it is given that weight is balanced by vertical reaction force. Vertical reaction force. So here if you see, this is a cylinder and then it is supported over a wedge and you need to find what is the reaction force. So you have the idea of, so what is the reaction force? It is rho g into, that is what is called the center of gravity into area. So we don't know what is area because we know only the diameter because the cylinder we also know the length also. H bar we know that is your radius because this is the point of, if I project this area, it's a vertical plate and it is, this is the diameter, so half is radius. So this is given, rho is given, g is given. We don't know the area. So the clue is it is given that vertical force is balance the weight of the cylinder. So and also it is given that, okay, height and height is also given. What is the length? So length is given also 2 meters. So it is also given 2 meters. So therefore, vertical force is only balanced by the weight. Therefore, the only component that is remaining is the reaction force in the that will try to oppose the force by the liquid on the cylinder. So if I see it, it is area is pi dl and everything is given. So if we try to find out, rho is 1000 into gravity is 9.8 into area is diameter is 3 meter into pi into d that is 4, 2 into 2 into 2 again the length. So if you try to solve, you will get what is nearly the reaction force that is coming from the wedge and the okay. So it is and also like the area is not pi dl actually because it is a projected area, so it is d into l only. So it is 2 into 2 into 2. So sorry, I think this is also 3. So 2 into 3 into 3. So it is 9 to the 18. So if you directly solve it, we will get at around 530 Newton. So this is the force that is on the horizontal direction, and we need to take the projected area. Now the next question is, you know the metacentric height. So the question is related to the metacentric height, and uh, it says which of the following option is correct. Following options is or are correct. So the first question is metacentric height. So I am writing it MCH. Metacentric height of warship is greater than metacentric height of passenger. The second thing is the more circle representation of force acting on a body in a fluid which is at rest is a point. The C option is a glass filled with a liquid falling freely has zero pressure at the bottom. And your D option is the mosquitoes sit on the water due to surface tension. So which of the following options are correct? And it is or not, so multiple options can be correct. So I'm giving you 1 minute. Please think this. Which of the following options are correct? So the metacentric height, that is, it decides the stability of any object that is partially submerged in a liquid. So metacentric height for a warship is like if studied for the if metacentric height is large, that would lead to discomfort and larger amount of oscillations. Therefore, metacentric height of passengers is keeping low so that their comfort can be provided, although safety is little bit compromised. But for the warships, the safety is the prior thing. So metacentric height of warship is greater than metacentric height of passenger ship. That is answer is correct. The more circular representation of a force acting on a body in a fluid at which is at rest is a point. So if you draw, suppose you have a body and a fluid is at rest. So the more circular representation is if you say what is the force that is acting here, also the compressive forces act from all the directions and they are at same magnitude. Therefore, it is a point that is a compressive in nature minus sigma, and this is your tau. So this is a point, the more circular representation. So this is also correct. A glass filled with a liquid falling freely has 0% at the bottom. So suppose you have a glass filled with a liquid, okay, and it is falling freely. So if you just apply dp by dz, that is in this z direction, is equal to rho g, and here because of the gravity, it is g plus a of z, and a of z is negative. So this term is minus g, and this term becomes zero. Therefore, dp by dz is equal to zero, and hence that actually this is zero gauge pressure. So therefore, P is a constant all over the length. So if it is although filled with a certain height, but whatever P is here is same P is we feel here. And the fourth option is the mosquito sit on a water to surface tension. Yes, it is correct. And that's why we wall because the what you say suppose it is the same way that a needle is floating on the water because of the surface tension that this is a needle and surface tension acts and it counters the weight of the needle. So the next question is the question says the viscosity of fluid is measured by viscometer and it is constructed by a two concentric tubes. So one is this and another is this. And it says that the tube is filled in between the spaces. So if I say that the fluid is filled in between the spaces and outer dia is, I am writing as D0, outer dia, it is 15.25 centimeter and inner dia DI is this much, 15 centimeter. The length is 75 centimeter and it says that the inner cylinder is rotated at 200 rpm. So it is rotated at omega, that is 200 rpm, and it is consuming power of 16.8 watts. So you need to find what is the viscosity. So as you know that, and we need to assume that in between the plates, we need to assume the linear velocity profile. That profile is linear. So first we assume that it is linear velocity profile a plus y times b times y, and y the distance between them, and the boundary condition is at like y is equal to 0, uh, v is equal to omega r, that is uh, omega is given 200 rpm, so it is we can convert that. Therefore, a is equal to, that is a, so a is equal to omega r, and at y is equal to what is called as, suppose that the distance between them is h, v is equal to 0, that is a plus b into h. So if you solve this, you will get a velocity distribution. So if just you simply put, you will get what is called as, so if velocity is linear, you will get as, suppose this is velocity v and it is distributed in bit distance h. So it is v by h. So it says that you have velocity difference, that is I should write it in this way: du by dy is equal to, it is linear, therefore it is v minus 0 by h, and h is the difference, so it is omega r minus 0 by h. So if you solve this, you from this equation also you get the same expression. Now you know that tau is equal to mu du by dy, and mu is, v is what is called as omega r by h, and h is d naught minus di by 2. This is the distance in between d naught minus di by 2. Now, if you multiply with the area, you will get the shear stress that is acting. So, mu omega r 2 omega r by d0 minus di into the area is pi di into L. This is the internal area where the shear force is acting. Now, if you the power is force into omega, or sorry, torque into omega, and torque is force into what is called as R. So, if I just multiply it, torque into R into omega, so if you just say it is mu into 2 omega R by d0 minus di into pi di L. This is your force into R is di by 2 and into omega. So this is the power. So here you know that this is the viscosity that is unknown. Omega is known. R is what is called as di by 2. So everything is known in this equation except the mu. So if you just put the mu, you will get what is called as, uh, if you put everything, you will get the viscosity of the fluid. So I will give you the answer. The viscosity is, yes, the viscosity is coming as 0.024 Pascal second, or yes, it is 0.024 Pascal second. Now the next question is, it says that you have a hinge at this point, and a rod is maintained to avoid the flow of water, and a support is there so that it will not move, and this length is 5 meter. This is your surface, and water is not from the top, so it is exactly not from the top. Surface is at this point, and this is 4 meter, and you need to find this reaction force from this gate. So if you say this is the reaction force, so what is the reaction force at this point? So as you know, this is again a force of a force over a vertical cylinder, that is rho g h bar into A. So if you say the the plate width is 5, so it is 5 in length, and yeah, so this is 5 in length, and for I also 5 in this width. So so as we all know that from the surface, the force will happen at 2 meter from the top. So, and the area is this area, that is 4 into 5, that is 20. So if we say force is equal to, this is 1000 into 9.8 into the h bar is 2 into area is 4 into like 5, it is 20. So you will get this much amount of force. So if I say 20.400, so 400 kilonewton. Now it says that what is the reaction force. So we will apply the torque at this O point. So applying torque at O and equating that equal to zero because there is no any motion that is happening. So summation of torque at O. So it says that this force this force happens at center of pressure that is equal to what is center of gravity plus Ig upon Ah square. So if you just put center of pressure, center of gravity is 2 plus 1 by 12 into the vertical length is 4. So 4 cube into what is called as 5 divided by the area that is 4 into 5 into what is h is 2 square. So this is the S center of pressure. Now this is the force that is acting at this point. So then your total force into what is called as center of pressure is equal to reaction force into that is the length of the tube that is 5 meters. So you will get length is equal to force into h of center of pressure divided by 5. Now everything is known in this equation, so we will directly put and get the value. Uh, let me uh, let me see what the answer is. Mm, So it is this is around 2.67 meter from the surface, and so actually this from the hinge, this distance is from this center. So from the hinge it is SCP plus 1 because you see that this one we had left, so the distance is that total. So if you just put and solve, you will get a reaction force of 288 kilonewton. So like this is the from the first chapter we had solved like much of the problems. Now we will go with the second unit and try to solve some problems that is from the streamlines and street lines. So if you remember in the acceleration term, okay, so uh, we need to write how the acceleration. So acceleration in ax, ay, and az. If you write, it is for if suppose velocity u v w in x y z direction. So it is written as W by del t plus U del U by del x plus V del U by del y plus this del U by del z. Similarly, for y is del V by del t plus U del V by del x plus V del V by del y plus W del V by del z. It is del U. And this is del W by del t plus U W by del x plus V. This is the same expression. Now, how we write this in vector form? So the question is, how can we will write this vector form? So in vector form, you will write as del v by del t plus v dot divergence of your v vector. So in this way, we will write. So if you just expand this, you will see that this term is a dot product. This is a divergence, and this is dot product. This will give. So this term will give particularly if we avoid the v, it will give u dd by dx plus v dd by dy plus w dd by dz. And because it's a vector quantity, it will multiply with this with I, j, k gap, and you will solve this. Also in what you say in a tensor part, it can be written as del ui by del t plus ai is equal to plus it will be v dot. This is written as uj del xj of vi ui. So it is written in this form. In the tensor part, it is called as initial notation. So ai is del ui by del t plus and I can vary from 1 to 3 and j can vary from 1 to 3. So this is called as initial notation. So from this we have a question that we have a velocity field that is given as zero point 0.5 plus zero point 0.8 x I cap plus 15 minus zero point 0.8 y times j cap, and you need to find what is the acceleration at point of 2 comma 3. So if you just simply apply the formula and just for your convenience I will write once. So it is a two-dimensional flow, so I will write only two-dimensional part. So if you simply solve, you will get what is called as this quantity as 1.68 meter per second square and this quantity as 0.720 meter per second square. And therefore, the total acceleration is in vector quantities. It is 1.68 I cap plus 0.720 j cap meter per second square. This is the answer of so what is the acceleration at the point of 2, 3. Um, so the question is, you have velocity field that is given as u naught plus bx times I cap minus dy times j cap, and it says that what is the streamline equation for this respective flow field. So this is the flow field equation, and you need to find what is the streamline equation. So streamline equation, if you remember, it is del x by u by del y by v. So it came from the equation of v cross ds is equal to 0. This is the equation of streamline. And if you solve as ui cap plus vj cap plus wk cap cross dxi cap plus dyj cap plus dzk cap and is equal to 0, you will get expression like this. So here it is a two-dimensional, so this term will not be exist. So dx by u is equal to dy by v. So dx by u naught plus bx is equal to dy by minus dy. So if you integrate this, this will be ln u0 plus bx by b equal to ln minus by. So minus will come outside if I just take this one by b. So this one will go, and if you just put it here and ln this plus ln by is equal to 0, and it will be multiplied u naught plus bx into by is equal to 0, and this is equal to 1 because ln1 is equal to 0 into by is equal to 0. So y is equal to uh, second, let's see. So just a second, I'm seeing the what is the correct answer. Okay, so the answer is, if you simply solve it is so this b will be here. So it is 1 by u naught plus bx into b. So this is what is this is lf. So if you just take it out, it will be 1, and it is this is the answer. Now we have a next question that says, so we have one question that says, suppose there is a stream function and there's a potential function. So we had discussed this much. This thing is in a very large. So if is there if if stream function exists, then flow is rotational or irrotational, and if potential function exists, then again the same question. Flow is rotational or irrotational. So the thing is, if a stream function exists, then it only satisfies a continuity equation. And for the flow is rotational, irrotational, it doesn't say anything. Therefore, flow can be anything. Flow can be rotational or irrotational. The next question is if it and for flow to be irrotational, omega z is equal to we say del v by del x minus del u by del y, and if you put the stream function, it will be del square psi by del x square plus del square psi by del y square, and it should be equal to zero to be irrotational. Okay. Now in this function, potential function is exists only for potential function exists only for irrotational flow. Okay, so this is the main difference. Now the next question is there is a flow distribution, and flow distribution is given as v is equal to the vector is equal to y I cap plus x j cap, and it is saying that what is the equation of streak line, and it is not asking what is the equation of a streak line, what equation of a streak line represents. So what it represents? It represents a circle or hyperbola or parabola or ellipse. So you know that the equation of a streak line is given as del x dx by. Okay, so the thing is, as you can see that this is a steady flow, therefore, therefore, streamline, streak line, and path line will coincide. Streak line, streamline, and path line will coincide. Therefore, if you solve any of the equation, you will get the answer for everything. So we'll solve the streamline equation. Dx by y is equal to dy by x. So it is x square by 2 minus y square by 2 is equal to constant. So this is the equation of hyperbola. So therefore, the streamline represents or streak line represents the equation of a hyperbola. Now from again, we will try to look into new things. This is now we will look into mm, some of the from the fluid dynamics, and so the thing is, what is Reynolds transport theorem, and what is the application of Reynolds transport theorem? So it says like um, what is the need of the Reynolds transport theorem? So the thing is, it will it will uh, or I should write it bridge the um, system laws to control volume by some modification. So it simply means that you have a Newton's law of motion or for a system that says it is rate of change of momentum, but you cannot apply this to a control volume, so it will change the law from a system to a control volume. So this is another transport theorem. Now the second part is if beta is if if beta is some intensive property, then what write RTT for beta for a control volume. So d of dt of dt of beta into what is called as meta into rho into dv. This is your system approach that is equal to del of del t of integral of beta rho dv for the control volume plus integral of the control surface rho beta v dot n cap dA. So you know this is rate of change of rate of change of beta in con- in a system is equal to rate of change of beta in control volume plus the efflux going out of control volume, going out and coming in of control volume. So this is the expression. Now the second thing is what is what is the continuity equation? Write it in scalar form, in vector form, and in initial notation. So you know the continuity equation, it looks like this. So this is your scalar form. Now if we try to, there is also one form that is called as d rho by dt plus del x of u plus del y of v plus del z of w. So this is again another form. The third form is del rho by del t plus divergence of rho v is equal to 0. So this is a vector form. Again, this can be represented in this way. Divergence of v is equal to 0. The third form that is called the initial form is plus del x j of rho uj equal to 0. So it can be written in this form also. So this is an initial notation. So this is all the these are expression of what is called as continuity equation. So all forms of continuity equation. Now the next question is um, it says that so the yes, so suppose you have a velocity that is given, so you have a v velocity that is your total v velocity vector has a u I cap plus v j cap. So this v is given as v is equal to y square minus 2x plus 2y, and it says that flow is steady and incompressible. So you need to find what is the velocity of u, and it is flow in 2D plane. So the first thing is, if it is incompressible and steady, this equation is satisfied. Now, if I write del u by del x plus del v by del y, so if it differentiate, it will be 2y plus 2 is equal to 0, and del u by del x is equal to minus 2y minus 2. And if you integrate with respect to x, we will get minus 2yx minus 2x plus some constant. So this is like the expression of a u component. So the thing is, the constant is not known. It can be any function of y. So, so your velocity can be like v complete velocity is minus 2yx minus 2x plus y. This is in I cap. Actually, I need to write also that this can be any function of y, and the equation is minus 2yx minus 2x plus any function of y into I cap plus y square minus 2x plus 2y into j cap. So this is your complete velocity. If the question is given, it is incompressible. A question, you know that with the velocity profile for a turbulent flow is V max into y by r0 raised to the power 1 by 7. It is the velocity with a pipe diameter of pipe radius of r0. It says in this way that the velocity varies in this form, and r varies from 0 to small r0, and okay. So y is the distance from the wall, and we need to find what is called as what is the ratio of average velocity to maximum velocity. So actually we need to find the ratio of average velocity to maximum velocity. So for that, take suppose this is your tube. Take an elemental strip at some small distance r with a thickness of dr. So the thing that is, what is your mass flow rate dq or volume flow rate? It is velocity into area. So velocity is v into dA, or velocity is given as v max y by r0 raised to the power 1 by 7 into the area is 2 pi r dr. 2 pi r dr is the area over which the flow is happening. So if we say that density is not a function of y, and this y can be changed as r0 minus r, because this y is from the wall. So if I take r0 minus r, it is from the center. So it is v max into r0 minus r by r 1 raised to the power 1 by 7 2 pi r dr. This is your small flow rate. And if you integrate dq, this is the total flow rate. Q is equal to 2 pi v max. And here the integration is r0 minus r by n. R0 raised to the power 1 by 7 into r dr from 0 to r0. And if you just integrate it, you will get a value. Um, you will get a value, and then you know that so this is your what is called as total flow rate, and your average flow rate is q by total area. So it is this quantity q by pi r square. Therefore, if you solve V average divided by V max, you will get as 0.817. This is for the turbulent flow. And if you remember the V average by V maximum for a laminar flow for a pipe, it is around 2. So this is the answer. Now, moving to the next question. So you have a question. Okay, so next question is, it is given that this is a plate that is suspended by a nozzle. That is, no, this is your nozzle, and the water is going in this way, and it is sustaining this plate. And this is your, so this is your inlet diameter. This is your outlet diameter, and inlet and the mass of the plate is 20 kg, and is suspended by a stream of jet of water at a height h. So this is the height h. The velocity of jet is 10 meter per second. So the velocity of a jet is 10 meter per second. Nozzle exit diameter is d exit, that is outlet diameter is 60 mm, and density is 1000 kg per meter cube. And it says that what is this equilibrium height to the diameter of jet, ratio of this equilibrium height to the diameter of jet. So we need to find what is this equilibrium height to the diameter of jet if g is given as 10 meter per second square. So a flow is happening, and because of its diverging section, it sustains a plate of mass 20 kg, and you need to find that is going above a height of h, and you need to find what is the height h divided by the diameter. So this is the sorry, nozzle exit diameter is 60 mm, so this is d exit, that is d1. So this is d1. You need to find what is the outlet diameter, and the inlet velocity is given as 10 meter per second. So first, what is the volume flow rate? Pi by 4 d square into v of jet. So if you solve, you will get as 0.02827 meter cube per second. And if you say that the flow is incompressible and density is not changing, so the force that is exerted by by the section will tend to lift the plate. So the force that is this 20 kg into 9.8 will lift the plate, that is mass, into what is called as V out. So that is rho into volume into, this is the volume into V of out. So this is the force that is exerted. So density is 1000. Volume is given as 0.02827 into velocity of out, we don't know. So it is 20 into 9.8. So out velocity at the second point is given as, it is given as 7.07 meter per second, and therefore this is 1 and 2. So applying the equation of motion, v1 square is equal to vt square minus 2gh. So against the gravity it is flowing, therefore h is equal to 2.5 meter. Now, what is the diameter at the outlet? So you know that mass, whatever is going in, will go out. So if density is constant, it is velocity into a1 is equal to v1 a1 is equal to v2 a2, and it is 10 into pi by 4 into 60 mm, so 60 square is equal to 7.07 into 5 by 4 into d square. Therefore, d is coming as 71.3 mm, and therefore your h by d ratio is around 35.05. So this is what the answer is. So now I will give you one problem. So here this. Okay, so the question says, what is the vector representation of Navier-Stokes equation? So what is the vector representation of Navier-Stokes equation? So just think about it. I will be here in 5 minutes, giving 5 minutes break. So we will. The question is, what is a vector representation of the Navier-Stokes equation? So um, first of all, what is the Navier-Stokes equation? Navier-Stokes equation is just a momentum equation for a controlled volume, and there are many assumptions that have been made. So first, we will make the what is the vectors like vector equations? Rho del v by del t is equal to minus grad of p plus rho of g plus mu del square v. So this is the vector equation in which this is a this is your what is called as acceleration. It has two components, that is one is temporal and one is convective. Then this is your pressure gradient term, pressure gradient. Then this is your gravity head, and this is your viscous force. Okay, so this is what is called as vector representation. If you write in the what you say in that initial notation, you will write as del ui by del t is equal to minus del p by del xi plus rho times gi plus mu times del x del u by del ui by del xc. So it is written in this form. So this is the initial notation where I varies from 1 to 3 and also J varies from 1 to 3. So this is the expression. Um, now the question is given as streamline function is given as 2xy, and you need to find what is the potential function. So it says that both exist. Now you know that for streamline potentially both exist, then velocity is equal to minus del psi by del y. That is equal to in potential function that is equal to minus del psi by del x, del phi by del x. V is equal to del phi by del x, that is equal to minus del phi by del y. Now you have two equations. You can solve this. So this equation you know from here, it is 2x minus is equal to minus del phi by del x, and minus will go away, and phi is equal to x square plus some constant. And it is function of y because it is with respect to x. Now, if you just simply put this equation, you will get del psi by del x is 2y, that is equal to minus del psi by del y, and you again integrate, you will get y square minus just some function of x. Now you have two equations. One equation is this, and then another equation is this. Now you can club these two equations, and you will get what is psi is, that is x square minus y square. This is the what is called as the potential function phi. Now we have a next question that says a fluid of viscosity. So in a pipe, a flow is happening in which the fluid viscosity is given as 0.7 Newton second per meter square, and specific gravity is rho is 1.3, so it is 1300 kg per meter cube. Then the diameter of the pipe is 100 mm, so diameter is 100 mm. And the maximum shear stress on the wall is tau max, that is given as tau max is given 196.2 Newton per meter square. And you need to find what is the average velocity. So first of all, the shear stress on the wall, if you know the relation, it is dp minus dp by dx into r by 2. So this is the equation that we will use to obtain the dp by dx. So because the flow is happening because of pressure gradient, we can now know what is the pressure gradient. So tau 0 is known 196.2, that is equal to minus dp by dx into r is 50 mm, that is 0.050 divided by 2. So you will get dp by dx, that is equal to 7848 Newton per meter square. Now you know the dp by dx, so u average is given as 1 by 4 mu, or sorry, 1 by 8 mu del p by del x minus into r square. So 1 by 8 into mu is given as 0.7 minus dp by dx is 7848 into r square, it is 0.050. So u average, therefore u average is equal to 3.50 meter per second. So this is the solution. So the next question is, for laminar flow in a circular pipe, what is momentum correction factor and energy correction factor? So uh, for this, you need to know the velocity profile. So for laminar flow, you know that it is a quadratic profile. So momentum correction factor is, so you have actual momentum, that is transferred, divided by the average momentum. So 0 to r, the what, so it is mass into velocity. This is momentum. So you need to differentiate mass rho into 2 pi r dr. This is your area into u, that is velocity. This is mass into u square. So this is momentum divided by uh, m into u average. So this is what is the momentum correction factor. So if you know the velocity profile, so if you know we have velocity profile as minus dp by dx into r square minus r square. So you know this is the velocity profile. So you will directly substitute and integrate over with respect to r. You will get momentum correction factor. Momentum correction factor is 4 by 3. And energy correction factor, similarly, energy correction factor is 0 to, so it is half mv square. So if you just make it in the form of differential elements, it is rho into 2 pi r dr into u cube divided by half m into u average square. So this is the momentum correction factor, energy correction factor, and SOLUS 2.0. So this is the value you can solve because we know the velocity value you can put and we can directly solve the equation. So um, So the next question is, okay, so the next question is, a capillary tube is used to measure the viscosity of a fluid, and it says the diameter of the tube is 40 mm, oil of specific gravity. So oil is stored of a specific gravity 0.5 and collected externally in a tank at a rate of 40 kg in 2 minutes. The pressure the pressure head difference between the ends. So you that tube is like this. So at the end, the pressure head difference is delta P is zero point 0.3 meter of water, and the length of the pipe is 1.5 meter. And you need to obtain what is the viscosity mu. So first of all, it is a flow in a pipe. So you know U is equal to 1 by 4 mu del P by del X minus into R square minus R square. Then you take the average, it will be 1 by 8 mu minus del P by del X into R square. Now we have the mass, we have the density, so we can obtain the volume flow rate, that is 40 divided by 0.8 into 1000, that is 800 into 2 into 60. This is in meter cube per second. So this is the volume flow rate. Now U average is Q upon 5 by 4 D square. So this is your U average. So this value, if you solve, you will get U average as, um, if you solve it, you will get the value. And then you just put the U average on this section and you will get the viscosity. So viscosity that is coming is 0.295 Pascal second. So like this is, now we will try to look in the losses part. So in the Moody's chart, I am drawing a representation of, so here we have a parameter A, here we have a parameter B, and the graph looks like this. And here we have a parameter C. So the question is, what are the parameters A, B, and C? So this is the smooth tube. What we called as A, what we called as B, and what we called as C. So if you look at the Moody's chart, you will find that this is what is called as the friction factor. B is called as the Reynolds number, and this is called as the relative roughness. Relative roughness. That is epsilon by it is surface roughness divided by the diameter. So this is surface roughness divided by the diameter. So this is the one question. Then we have another question, that is, in turbulent flow regime, inside the pipe, um, inside the smooth pipe, what is the friction factors value? What is the correct friction factor value? So as you know, it depends on the only the Reynolds number. So it is 1/5 power of the Reynolds number. This is the answer. For laminar flow, it is 64 by Re for laminar. And it only depends on the, for a smooth tube, it only depends on the Reynolds number. Now we have another question that you have four identical pipes. Like this is your, you have four identical pipes of diameter D and length L are connected. What is the equivalent length of pipe for double diameter single pipe? So suppose this is the end one and this is two. So suppose you have a new system that in that we have a double the diameter, and the condition is delta P1 to 2 in old is equal to delta P1 to 2 in new. So this is the condition. So first of all, the old system, what is the total friction pressure drop? So if you say delta P divided by rho, it is the head in the old system, that is equal to HF1 plus HF2 plus HF3 plus HF4, that is equal to FLV square upon 2GD plus the same thing. So it is 4 FLV square upon 2GD. So this is what is the pressure drop. Now in the new system, the same head loss would be there. So new system is H new FLV square upon 2GD. First of all, the mass remains the same for both the systems. No, the pressure drop remains the same. The mass can change because the diameter has changed. So if that both are equal, FLV square upon 2G and D is 2D, double the diameter. So the length is, if you simply cut everything, the length is 4L D raised to the power 5 into 2D, and FLV square upon 2GD. So also you can just you need to convert this velocity to the mass, because for the both the system the mass will be the same. This velocity is mass divided by the area of cross section into rho. So if you just simply put, you will get as the old system is FL, and the mass, that is you say, or volume square Q square upon it is in the form of D raised to the power 5, D equivalent raised to the power 5. So it is directly proportional to this. So if you just equal the both the systems, FL is Q square upon D5 into 4. So the new length can be written as 2 raised to the power 5, because it's double the diameter, into 4L, that is equal to 2 raised to the power 7L. So this is the new length for which the friction pressure drop is same and the same flow rate. The next question is a crude oil. So you have a crude oil of a viscosity, kinematic viscosity of 0.54 strokes is flowing in through a tube of a diameter 0.3 meter at a rate of 0.3 meter cube per second. And it says that the pump is required to transfer this to a 1 kilometer distance. L is 1 kilometer, and rho of oil is 700 kg per meter cube. And you need to know what is the power that is required to transport. So you need to connect one pump here. So the thing is how much power is supplied to the pump, or what is the desired power so that the crude oil can be transported to 1 kilometer distance. So first find the Reynolds number, rho Vd by mu or Vd by nu. And if you solve, if you take the Reynolds number, it is 3 to 3.18 and this to the power 4. Because 2 is known, you simply divide by V q by A, that is equal to V. So you can get a velocity and you put here that is much greater than 2300. Therefore, it is turbulent region. Now, because it is a turbulent region, we will use a formula of turbulent flow. The friction factor is 0.079 upon R e raised to the power 1 by 5. Now, the Reynolds number we know. So simply if you put the Reynolds number, you will get 0.006. This is the friction factor. And now the head loss is given as 4 FLV square upon 2GD. So if you multiply, it is 0.006 into the length is 1 kilometer, 1000 meter, into the velocity that we will find out is 4.24 square divided by 2 into 9.8 into what is the diameter, it is 0.3. So you will get a head loss of 73.2 meter. Now delta P is rho GS, so density is 700 into G is 9.8 into 73.2. So this is total, you get around 502.15 kilopascal. Now power required is pump power required is delta P into Q. So the flow rate into the pressure drop. So 502.15 into Q is 0.3. So you will get a nearly 150 kilowatt of pumping power that is required. Now we have another question. You have a pipe and there is sudden enlargement that is happening here from 100 to 200 and if at this location the velocity is 8 meter per second, so we need to find what is the pressure drop at this location because of sudden enlargement, and density is given as 1000 kg per meter cube. You need to find what is delta P. So first of all, if you apply the continuity equation between the point 1 and 2, you will get what is the velocity of the second point. So applying continuity equation, rho A1 V1 equal to rho A2 V2. So you know this for the incompressible flow, rho can be cancelled out. A1 V1 equal to A2 V2. So area is pi by 4 d square, that is 100 into 8 is equal to pi by 4 d2 square, this is V1 square into V2. So V2 can be obtained as 2 meter per second. Now you know your HF value is V1 minus V2 whole square divided by 2G. That is a head loss because of the sudden enlargement. So V1 and V2 we know it is 8 minus 2, that is 6. 6 to the 36 divided by 2 into 9.8. And this is a head loss. Now delta P is equal to rho into G into H, that is 36 by 2 into 9.8 into the water is when it is of density 1000 into 9.8 again. So you will get around 18 kilopascal. Like this is the pressure drop that is happening in between the ends, in between the sudden enlargement. Now the another term thing is, so suppose flow is happening It says question is the maximum power transmission efficiency from the pipe and the head loss so it is so it is saying that you are transmitting a liquid. For that certain power is required. Now, what should be the maximum power, like maximum efficiency for this transfer? So, like efficiency is defined as this is the total head minus the head loss divided by the total head. This is the efficiency. Now, power is delta P into Q. So, it is H minus FLV square upon 2 GD. So, this is the head loss, that is the pressure drop into Q into rho G. This is the available head into what is now you know the power, so you can differentiate the power with respect to velocity and equal to zero because here is also velocity, here is also velocity. Then you will get the head that is required, that is equal to 3 HF, and HF is equal to H by 3, and the maximum efficiency is 66.67%. This is the answer. Now the another thing is we have a rectangular passage and air is entering. It's a 7 meter long section. Air is entering at of the size is 0.15. Sorry, it is 0.15 to 0.20, and it is entering at the velocity is that is 7 meter per second. Temperature is given as 35 degrees Celsius, and pressure is 1 atmospheric pressure. Now the it is said that we need what is the fan power that is required to transfer the air if efficiency of fan is 95% and mu of air is 1.8 in 10 raised to the power minus 3 pascal second. So here we have given the what is called as mm, velocity. So first we will find what is the Reynolds number. So Reynolds number is rho v d by mu, but we don't know the diameter. So we need to find the hydraulic diameter, that is 4a by p. Area is the flow area and this P is the wetted parameter. Therefore, it is 4 into area is 0.15 into 0.2 divided by the wetted parameter, is the parameter of the surface, 2 times L, L plus B, that is 0.35. So if you solve, we will get 0.172. Now, density we don't know, therefore we will apply the ideal gas equation because air can behave as ideal gas and you will get around 1.13 kg per meter cube. And if you put the Reynolds number, rho is 1.13, velocity is 7 meter per second, diameter is 0.172, divided by the mu, that is 1.8 and 10 to the power minus 3 for the air, you will get a Reynolds number of 76,000. That is much greater than 2,000, so it is a turbulent regime. Therefore, friction pressure drop is 0.079 divided by RE raised to the power 1 by 5. So 76,000, oh sorry, so it is 0.079 divided by 76,000 raised to the power 1 by 5. And if you solve, you will get a head loss friction factor of around 0.00476. Therefore, HF is equal to 4 FLV square upon 2 GD. So every term is known. Simply the 1.94 meter of air, this is the head loss. Now the power that is required is the power that is required is power is equal to delta P into Q. Delta P is given as HF into rho of air into G and into the volume flow rate. So it is pi by 4 d square into pi by 4 d square into velocity. Now if you solve this, you will get a value of around 4.5 watt. So this is the power that is required. Now efficiency of the fan is given as 95%. Therefore, power actual that is required as 4.5 ideal power divided by 0.95. So you will get a 4.7 watt. That is the actual power. So I hope this solves your problem. Today we have solved much of the many problems, and please solve the question before the exams. So in this rectangular type sections or in this rectangular type problem, you need to find the hydraulic diameter. Hydraulic diameter is a 4A by P. So suppose if this is a open channel flow. So here, suppose the open channel flow, the flow area remains the same. It is, suppose this is L, this is B. So area remains the same, that is L into B. But the parameter will change, that is 2 times B plus L, because you have B and B this side, but length at this side. So this is the weighted parameter, and that is why it is changed. For the rectangular section, for the square section, you will see it is the weighted parameter or hydraulic diameter, that is very important. So hydraulic diameter, that is DH is equal to 4A by P. For different sections, we need to find the hydraulic diameter to know the Reynolds number, and then only the flow can decide that whether it is laminar or turbulent. So I hope this solves your problem. We will meet in the next class. Uh, Thank you.